Let's talk about implicit differentiation. Last time we talked about the regular differentiation. By that, we start with a usual function y equals fx, and we apply various formulas and differentiation rules to compute, including the chain rule, which we talked about with a few examples. Now, sometimes the function is not written explicitly, rather it is an implicit function. Let's look at an example. Suppose we have an equation x squared plus y squared equals to 25. Therefore, this implicitly defines a function y as a function of x, so y equals fx. We want to find the derivative of y with respect to x at the point 3 minus 4. You can easily check that this particular point 3 minus 4 is indeed on the curve. So to do that, well, let me actually show you the picture of the curve. And it's well known that the curve for this equation is simply a circle. Center is the origin, radius is 5, which is the square root of 25. And obviously the point we're talking about, 3 minus 4, is right here. And basically we want to find the derivative at this point. In other words, the slope of this tangent line. You should be able to visualize that y is a function of x, which will be part of this curve, which is the bottom half. This implicit function defines two different functions. One is the upper half semicircle, the other one is the bottom half semicircle. Alright, so to do this implicitly, we start with the equation. So just rewrite the equation here on both sides, and then take the derivative with respect to x on both sides. In other words, you take a d dx on both sides. I should say d dx, not necessarily dy dx, but just d dx on both sides, and which will involve dy dx. Alright, and if you look at the first term, which is x squared, it obviously gives you 2x. What about y squared? Well, you would like to say that's just 2y, but that is not completely correct because y is a function of x. In other words, this is a composition function. It's kind of like a gx squared. And when you take the derivative, you would get 2y, which is followed from the power rule, times y prime, which is part of the chain rule. The right-hand side is obviously 0. So it's useful to note that if you have y squared, take the derivative, and you get a 2y y prime instead of simply a 2y. And then you simply solve for y prime from here, from this equation, and you get y prime equals to minus x over y. Basically, by moving 2x to the right-hand side, cancel out the 2, and then divide both sides by y. And then you substitute the values, 3 minus 4, and the final answer is 3 over 4. Fairly simple. Those who have some extra energy, extra time, and interest, you can try to solve this problem in the traditional way. Namely, you can actually solve for y, and then compute the y prime. So let's go back to the graph here. You can solve for y by looking at the bottom half of the solution, and that's why you get y equals to negative square root of 25 minus x squared. Basically, you move x squared to the right-hand side, taking square roots on both sides. Why do you have the negative sign? Because we are looking at the bottom half of the circle. Now, to take the derivative, apply the chain rule. More specifically, the generalized power rule that I mentioned the last time. And you just rewrite the square root in the form of 1/2 power. This helps people to visualize this is a power. And to take the derivative, you just apply the usual chain rule which means you bring the 1/2 to the front and then subtract the power by 1, so you get a negative 1/2. And then you apply the chain rule, which says you need to multiply the derivative of the inside, which is a minus 2x. Now, this looks not quite the same as the previous answer that we got, which is minus x over y. Can you visualize that they are actually the same? They are. I mean, I'll leave it to you to think about this. Once you cancel out the x, the 2, then you start to see x on the top. That x is the same as that x here. And then this part here, the negative 1/2 power, you can move that to the denominator. And you take that as a square root of 25 minus x squared. And that is exactly what y is equal to. Negative y, actually. And so you can see they are the same. But anyway, if you substitute the numbers, x and y, and you will get the same answer eventually. This is a rather simple example. I do encourage you to practice more complicated examples. And in all those examples, you should remember the kind of basic rule that is, when you have something involving with y, you need to use the chain rule. For example, y squared derivative should be 2y times y prime, rather than just simply a 2y. Let's move on and talk about the next topic, which is related rates. I think those two are naturally related. So, related rates and the implicit differentiation, they are naturally related. Let's give a comparison here. So, implicit differentiation, well, you start with a implicitly defined function written by equation in terms of x and y. So, let's denote this by capital F x y equals 0. How do you find the derivative of y with respect to x? Well, you take a d dx on both sides, and then you solve for y prime from that equation, just like the example we did a moment ago. What about related rates? It's almost the same. You start with a function, the equation between x and y, so f x y equals 0 like before. However, this time, x is a function of a third variable t. So rather than simply writing x, you're going to write xt. And y is a function of t as well. So you have f xt yt equals 0. Well, the basic question for those kind of problems usually try to find the dy dt, given that dx dt and given other data. How do you do that? Well, you take d dt on both sides, instead of taking d dx as before. Let's look at an example. This example is naturally related to the previous one that we just saw. Suppose we have xt squared plus yt squared equals 25. And at a particular moment, t equals to 10. Suppose x equals to 3, y equals to minus 4, dx dt equals 7. We want to find out dy dt. So we previously saw that this equation is a circle. So to show you a picture, let me just show you the picture first. So here we do have a circle here. And at this particular point, 3, 4, we are talking about right here. And dx dt basically represents the speed, the change of rate, or the speed of x component. So imagine the particle is moving on this circle, and t is the time, and we know that dx dt equals 7. That means if you look at the projection of the particle on the x-axis, it is moving at a rate of 7. So by the way, you may want to think about whether this point is moving counterclockwise or clockwise. I will let you think about it for a few seconds. All right, perhaps you can see that it's actually moving counterclockwise, and that is because dx dt, which equals 7, is a positive number, so you'd have to move that way rather than the other way, which means the point has to move this way. Okay, let's start solving the problem. So just like before with the implicit differentiation, you would start with rewriting the equation, which is x squared plus y squared equals 25. Now, instead of taking d dx as before, you're going to take d dt this time. Therefore, when you have x squared, you're not going to get simply 2x. Instead, you're going to have 2x times x prime, where x prime is really dx dt. All right, you do the same for y, and therefore you get a 2y y prime. And 25 gives you 0. All right, then just simplify the algebra, dividing both sides by 2. You get x prime plus y prime equals 0. Remember, you want to solve for y prime. So you put all the data into this equation. X equals to 3, x prime equals 7, y equals to -4, and keep y prime here. And then solve for y prime. And y prime is equal to 21/4. And this is the picture that I just show you. That's all. There are more involved problems, but those two examples gives you the basic idea in those two sections.